My name is Kayam Sheikh from Comms Division D. I will be presenting my case study on the IB distributed file system. This presentation will cover the background, architecture, design services, advantage and comparative analysis of IB, as well as its relevance to the modern distributed computing system. DFS allows users on a network to access files as if they were stored locally. It abstracts the underlying complexity of the data distribution, replication, and fault tolerance. Initially, the file system was simple sequential storage on tapes, which later evolved into hierarchical systems like Multics and the Unix, introducing directories and structured organization. The key challenges driving the development of the DFS were providing multi-user access across machines, ensuring consistency and fault tolerance, enabling global file accessibility without creating central bottlenecks. Looking at the historical timeline, the 1950s and to 1960s, the storage was flat and had no multiple user support. In the 1960s, the 1970s, hierarchical directories emerged in the system like Multics and the Unix, but these were still localized. The 1980s saw optimized local file systems such as the Berkeley's FFS and which were not distributed, but between the 90s, 80s and the 1990s, client-server DFS file system like NFS and the AFS appeared. Through centralized server introduced bottlenecks. From the 2000 onward, large-scale DFS like GFS and HDFS and IB focuses scalability, replication, and the fault tolerance. IB introduced in 2002 brought a major shift. It is a peer-to-peer multi-writer read-write DFS. Each participant maintains their log using a distributed hash table with no trusted central server required, ensuring cryptographic integrity. Its significance includes supporting concurrent multiple users in a peer-to-peer environment, preserving data integrity even in the untrusted settings, and demonstrating the use of DHT as a backbone for distributed storage. Now let's look at the architecture of IB and its core component. IB uses a peer-to-peer log structure design with no central server. Each participant maintains an append-only log of all file system operations. These logs are stored in a distributed hash table, or we can say DHT, which provides a scalable fault-tolerant storage for both logs and data blocks. The immutability of these logs ensure auditability and the data integrity. This design contrasts with the traditional DFS system like NFS or AFS, which rely on centralized metadata servers and can suffer from bottlenecks or single point of failure. The IB architecture is layered into three components. First one is the application layer, provides an NFS version 3 compatible interface allowing standard application to interact with the IB seamlessly. The IB layer that maintains per participant log snapshot version vectors and handles the conflict deflection. The DHash layer, the underlying distributed hash table, stores log and bottle data blocks, ensures application, and provides cryptographic integrity. Next, let's explore how IB ensures data integrity and manages logs. The dhash layer stores all data as key values pair. The keys are cryptographic hash of the content. The data is automatically replicated across multiple nodes, providing fault tolerance. IB uses two types of blocks: the content hash blocks and public key blocks. The content hash blocks, immutable block keyed by the SHA-1 hash of their content. The public key blocks, mutable blocks signed with the participant private key to ensure the authenticity. Each participant maintains a linked list of log records, which include inode, write, link, unlink, rename, set attributes, and end operations. The log head block always point to the most recent log entry and are signed to prevent unauthorized tampering. IB uses a version vector to capture each participant knowledge of the system. This allows the system to preserve causality and detect confliction even when participants write concurrently. For client-server interaction, IB is exposed via local NFS loopback server. Application can operate without modification, while all communication occurs through dhash using put and get operation rather than the direct peer-to-peer message. This design ensures secure decentralized operation while maintaining the compatibility with the standard application. Now we will discuss IB's file system design, focusing on data organization, metadata, and the storage. IB uses a log structured model like where every file system operation such as creating a file or writing data or renaming directory is recorded as a log entry. Each file or directory is identified by randomly generated 160-bit number, which is called I number, which also serves as the NFS file handler. This approach avoids the centralized metadata, instead reconstructing the global file system from participant logs. Metadata management in IB is dynamic. File length is determined by the highest write offset since the last truncation. The modification time is extracted from the latest relevant log entry. Link counts are calculated from link, unlink, and rename operations. This method provides flexibility and auditability, but it also increases the computational overhead during queries. Storage allocation and snapshots. IV uses snapshots, which are periodic, consolidated representation of the file system state. Snapshots include the file map, inode, data blocks, and the version vectors, and they are constructed incrementally. For example, every 20 new log records or every 60 seconds to improve lookup efficiency, and they reduce log traversal overhead. Namespace structure and views. IV uses views, which are immutable content hash blocks, and they list all participants' logheads and the root directory. View provides self-certifying name, which ensure authenticity. Membership is immutable and providing they prevent unauthorized change. Multiple view allow distinct trust domains and they support flexible collaboration in a semi-trusted environment. Let's cover the key services provided by IV. The file storage services. IV exposes an NFS v3 compatible interface supporting standard operations like creation, reading, writing, deletion, and attribute modification. File data is divided into blocks stored in dhash network with logs and these linking these blocks to maintain immutability. The write operation are optimized by deferring writes until file close, allowing parallel block writes and ensuring that all logs are immutable. The caching mechanism. The IV caches immutable blocks locally. They guarantees correctness without the risk of stale data. Version vectors enforce close to open consistency, while selective caching ensures that frequently changing blocks heads are not they are not cached, and only stable blocks are stored locally to improve performance. Replication and fault tolerance. At the rehash level, each data block is replicated across multiple nodes, typically three for durability. Log level resilience ensure that each participant's logs remain persistent even when offline. This design allows IV to survive node failure and recover from conflicting updates caused by partitions. Authentication and integrity. IV ensures that data integrity using content hash verification to detect tampering. Public key signatures on logheads to verify authenticity, and the IV agent they sequentially manages cryptographic keys, separating authentication from file operations. Access control. Unlike centralized DFS, IV model is decentralized. Participants decide which logs to trust. Ownership and permission bits are recorded in logs but enforced selectively. View restricts participation to authorized users, and encryption control unauthorized access even if data is widely replicated. And these services collectively provide secure, decentralized, and resilient file system operations. Now let's look at the advantages and limitations of IV. Advantages. IV is fully decentralized with no single point of failure. Each participant maintains their own log and dehashed application ensures high availability. Failures are localized and don't affect the whole system. From a security perspective, the cryptographic hashes and signatures guarantee data integrity, while self-certifying names and selective trust provide flexible control. In terms of scalability and collaboration, Ivy grows naturally as more nodes join, supports geographical distributed users, and require minimal administration. Finally, NFS version 3 compatibility allows standard application to operate with close to open consistency. Version vector detects the conflict effectively. Disadvantages. Performance is 2-3 times slower than NFS due to cryptographic and dehash lookups. High latency arise from remote lookups and log scanning. Log growth and snapshot cost limit while scalability for very large groups. Relaxed order semantics and manual conflict resolution are sometimes required. Operationally, there is no automatic user management and the system depends on dehash reliability. Overall, IV trades some performance for decentralization, security, and flexibility. Implementation and deployment. Ivy is written in C++ on FreeBSD, leveraging the SFS toolkit for event-driven programming and NFS support. The core component include the Ivy server, which exposes the local NFS file system. The Ivy agent responsible for managing private keys and signing logheads. The DHash server, which handles distributed storage and replication. And the NFS client connecting applicants to the Ivy layer. The configuration parameters are important for performance. Snapshots are taken every 20 logs or 60 seconds to reduce log traversal cost. The block cache holds 512 blocks to improve read performance. Replication factor is set to 3 for durability, and SHA-1 with key path ensure authentication and integrity. For mounting, IV uses self-certifying names derived from the hash of the view block, example /IV/hash. Deployment models vary. Small groups can operate locally without central coordination, while wide area networks have been tested on Planet Lab and RON nodes, supporting geographically distributed users. Tool and utility includes LC for conflict scanning, IV check for metadata repair, view management tools, log analysis utility, and key management integration. Performance highlights show that on a single machine, IV mean access time is like 18.8 seconds versus 7.6 seconds for NFS. Over WAN with 4 DHash servers, IV take 376 seconds compared to NFS 280.4 seconds. Bottleneck mainly come from cryptographic signing and DHash lookups. Real-world applications include distributed software development, academic research collaboration, mobile computing with intermittent connectivity, and semi-trust collaborative environment. In short, we can say IV design balances decentralization, security, and collaboration with moderate performance trade-offs. Comparative analysis of IV versus other DFS. IV differs significantly from traditional and modern distributed file system. Compared to NFS, IV replaces the client-server model with a fully peer-to-peer design, offering horizontal scalability and no single point of failure. Though at 2-3 times slower performance due to dehash lookups and cryptographic operations, its consistency is close to open, enhanced with version vectors, and trust is managed selectively using cryptography. Against AFS, IV provides a block-level caching with version vectors versus AFS whole file caching, and it scales naturally with peers instead of relying on server replications. Security is enhanced through cryptographic verification, and fault tolerance leverages dehash replication. In comparison with the GFS, IV targets general purpose collaborative workloads rather than GFS large sequential data. GFS uses a master slave design and relaxed consistency, while IV maintains the NFS like semantics while with partition tolerance. Latency is higher in IV, but it avoids centralized bottlenecks. Finally, relative to P2P system like CFS, PAST, or Ocean Store, IV supports multi-writer collaboration, trading off strong consistency for lower overhead. Performance highlights slow throughputs around 30 to 50 megabyte per second and latency from 100 to 1000 millisecond, constrained mainly by block scanning and version vector overhead. Overall, IV emphasizes decentralization, fault tolerance, security, and collaborative multi-writer support. Conclusion: IV distributed file system presents several key technical contributions. Its log-based architecture allows multiple users to update the system concurrently without central coordination. Like while cryptographic mechanisms like content hash blocks and the public key signatures ensure integrity and trust. The selective inclusion of logs supports semi-trust group collaboration, and version vector provides partition tolerance with conflict detection and reconciliation tools. IV impacts on distributed computing is significant. It demonstrates the multiple user read-write peer-to-peer file system are feasible without relying on Byzantine consensus. The use of distributed hash table as scalable storage backbone has influenced blockchain technology, collaborative platform, and edge cloud computing. Contemporarily, IV Designs aligns with cloud and edge computing trends. Its principles such as version vectors and selective trust have informed blockchain and the Web3 platform, guiding collaborative software and privacy-preserving systems. For system designers, the lessons are clear. Decentralization trades off performance, log growth, and vision vectors present scalability challenges, and the trust management remains crucial. Overall, IV serves as a proof of concept for decentralized, cryptographically secure, multi-writer distributed file system, and to architectural principle continue to influence modern system addressing trust, scalability, and collaborative challenges.